Hello, welcome, and thank you very much for coming and spending this wonderful evening here. I don't know, you're probably very interested in that topic, so I hope I will deliver. My name is Konstantin Ignatyev. Right now I work for the company Inspur, and it's a Chinese company, big company actually, not well known in US, but it's huge. And well, we're trying to learn from best examples and create systems for the Chinese market. But that's enough about the company. Let's talk technical. First of all, there's tons of stuff on YouTube, and you can always watch that. Right? So probably you're here for some interaction. Right? So please don't hesitate, ask questions. Presentation might get a little more chaotic, but it's not a lecture. Okay? So let's get started. So please raise your hand who knows about Kubernetes. Okay, everybody, almost everybody. Who's actually using Kubernetes or playing with Kubernetes? Way less. Okay. Who's working with Mesos? Okay. Who's working with Docker Swarm? One poor soul. Okay. All right. All right. So, what you want to hear? Overview or deep technical dive? What?
Real-time resources. Like real-time application or what to use in our current systems.
Okay. Well, it's probably a.
We're just, Konstantin, we're just looking at Mesosphere right now. I've dived into Mesosphere at our company, and I'm not sure if Kubernetes is an alternative or you can run Kubernetes on top of Mesosphere. So any input you have into why we would veer off Mesosphere and go straight to Kubernetes would be helpful.
Sure.
And I don't mind a technical dive.
Okay. Well, actually, my plan was to give the overview and explain things and then show them, kind of a reel. I normally shy away from doing the real things, doing the presentations, because things go wrong, but I will try. Anyway, let me explain what's going on. And first of all, I'd like to have a really bird's view of the landscape. So, I don't know who was working with the dreaded G2TE and various beans. There was a promise that one day you will pay money and you'll get a bean that will solve your business problem. Maybe accounting bean, maybe something else. Well, luckily we don't have those entity beans anymore, but now that promise actually came to fruition. There's lots and lots of suppliers, and they provide a solution for lots and lots of business problems. There's the providers of the infrastructure, and we still need three pillars. We need the computing, network, and storage. And on top of that, we actually need to deliver solutions for business problems with the minimum amount of efforts, with the maximum transparency and control over it. So these days, the level of abstraction raised really high. We can get those three pillars. We can provision computing and network and storage. From the bare metal, we can get the same things from the virtual machines, virtualized, network attached storage, and software-defined networks, and of course virtual machines. And these days containers are all rage. But fundamentally, whenever we want to do something, we need computing, network, and storage. And we want to configure them into something meaningful from the business perspective. So right now, it's similar to the MVC frameworks in the early Java days. That would be a framework of the day or framework of the week. These days, lots and lots of systems promise to simplify delivery. And I use a few examples. Go Paddle, then of course OpenShift. So they, some of them are, standalone things. The OpenShift from Red Hat is actually based on Kubernetes, and if you want to do something real, you still have to dive into Kubernetes. They try to create some abstraction level, but to my taste, it's not polished or that well enough. But time might tell. So there's lots and lots of such systems, and companies trying to build something on top of Kubernetes. And the topic of this presentation is about Kubernetes themselves and few supporting technologies, so you can judge, hopefully for yourself, if you need something on top of it, or if you will understand why, or maybe you'll be happy using Kubernetes. So there's another set of technologies we use these days. There's Chef, Puppet, SaltStack, Ansible, Terraform. Who experienced this, the Terraform, or heard about them? Nice. So, who don't know about that, the Terraform is a very nice declarative resource management system, and encroaches on some overlap with the configuration management systems. It's a matter of taste, but I think that Terraform in its declarative powers the most suitable for simple management of the infrastructure, provisioning of the resources, those three pillars: network, computing, and storage. And then we need some configuration management on top of it. It might be Ansible, or when we work with Kubernetes, we can delegate lots of configuration to it. So just why I like Terraform, because it's a simple declaration that we want a resource of a certain kind, give it a name, and give it a count. Lots of configurations look the same, but the way Terraform works is very intuitive. If now we decide, or some other controller decides that we need 5 or 15, we simply change count to 15, and we'll say apply. Terraform figures out if it needs to reduce the number of resources or increase the number of resources. It understands the state and just brings the actual state of the system in accordance for the desired configuration at this moment. So, let's dive into a technical details. So, nothing ground-shattering. It's a simple microservice, the Java microservice, that we want to create. Let's say we want to create inventory microservice, and it needs to be backed by the database, and of course the database needs to work against the storage, and so client. Nothing fancy. Well, however, these days everybody wants to have 24/7 availability. Everybody wants to have outage-less updates and rollbacks. And that creates lots of complexity. And lots of things can go wrong. You know, the network is not reliable. And if we want to scale horizontally, we need the load balancers here. Then we need to configure the whole thing. We need to configure our microservice, work with a database, but the database probably works on some node or machine that might go down, or maybe network communication again gets severed, and of course the storage. So that creates a complexity we need to address, but usually we are lazy, we just want things to work, right? At least I am very, very lazy. I'm okay spending some time configuring that, but then I want things to work, yes.
Not lazy, optimistic.
No, I'm honest, I'm lazy. And laziness is actually, engine of the progress. And by the way, my kind of development philosophy is CDD, convenience-driven development. Okay, so please keep this in mind for a little while, because now I will talk about Kubernetes, right? And then I will show how Kubernetes explode and support our little application. So Kubernetes does lots and lots of things, but it's all about delivering a robust foundation for our applications, or suites of applications. So we need a computer resource management. So we need to resource control, how much CPU, how much memory. We need the storage management. If anybody works of AWS and EBS, it can be mounted only once at one host. So when a host goes down, you want that storage to be remounted to a different host, and your, let's say, database provisioned there, so it will continue to work. Network management, load balancers and routers and SSL handling and certificate updates, all those things. We want them, and they are here. By the way, this diagram tries to map those fundamental things we need to the implementation details, how it's done in Kubernetes. For example, resource management is done through the namespaces and nodes. Nodes, it's basically machines where the Kubernetes run, and they can have labels. And for example, we have pool of resources, huge. Some of the machines are old, and we buy new ones, and some fancy ones with lots of GPUs for the Bitcoin mining or the new currency, whatever comes these days. So all we need to do is just join those resources to the pool, label them as high GPU or high memory or whatever the labeling system we want. And then when we deploy things, we can specify the label matching criteria and say, we want this process to work on the machines of this kind. For example, if we do the Bitcoin mining, we'll say, okay, give us plenty of GPUs. So then our process will be deployed on a machine that labeled as having those GPUs. Make sense? Any questions? So on the left-hand side, it's a snapshot of the Kubernetes dashboard that sometimes comes with Kubernetes, but can be deployed fairly easy. And I try to map things there. Then network management. It's the services that basically automatically Kubernetes create the load balancers. So even we have one node during the failover, it transparently connects us to where the new place our process is running, or when we add or remove nodes during, not the nodes, processes during the auto scaling. It keeps track of it, and we don't have to worry about that much. Logging and monitoring, also very important. Daemon sets. What's a daemon set is? Basically, it's a definition that we give to Kubernetes system. And by the way, everything in Kubernetes is YAML or JSON file, sort of a descriptor that says, I want this, that may be. So the daemon set is just one kind of a resource that tells Kubernetes that when we add node to the system, those daemon sets needs to be provisioned there. And usually, the most vivid examples are logging and monitoring. Before we do anything, we want to have logs. When things go wrong, we at least know something, right? So those will be provisioned first. They'll be started, and only after that, our actual workloads will be given to the nodes. Configuration management. Anybody familiar with the console vault? So it's not the full replacement, but can work really well. And there are config maps and secrets. They pretty much can take care of lots of not so secretive details. Maybe connection, credentials, maybe something, maybe some properties, debug levels. So again, we can give those descriptions to the Kubernetes system, and it will preserve that in actually it runs the etcd. In the production, you will have a cluster of those etcd nodes to ensure that everything we give to the system is preserved no matter what's happening, and has the backups and multiple copies. So we give the configurations, and then we can use that in many ways we see fit. We can mount those as files. We can expose the content of those secrets as environmental variables to the containers, or mount that single files or multiple files, or one file per key value pair. Are you following? Or is boring? So, okay, so one thing, the difference between, let's say, Mesos and Kubernetes. The Kubernetes, in my opinion, has a better architecture to support the usual things we do. In a Mesos land, it's more geared toward running long-term processes, and you have to jump through the hoops to run something only once, or a batch jobs. Kubernetes support that natively. You can deploy a batch job, and Kubernetes will try its best to make sure all the processes complete successfully, and that's where you can shoot yourself in the foot. You can deploy something, and if your process cannot succeed, just bug in the code, it will just keep trying and will eat your resources. But with good monitoring, you will see that. Also good support for running just one thing, just let's do that, when it's done, it's done. Or deploying a job and a cron expression, and then it will run periodically. It cannot, address very, fancy advanced scenarios, like possible with fancy schedulers or Hadoop things, but it can take care of lots and lots of things just by itself. And again, it has, in my opinion, right architectural abstractions. What we need: something to compute on, we need storage, we need batch jobs, we need just jobs, and we need scheduling, and we need the networking. Another thing that differentiates Kubernetes from, let's say, Docker or Mesos is that unit of computation in Kubernetes is pod. What is pod? Pod is one or more containers running together. They always deploy together. Again, it's a very convenient thing, so we can guarantee, when we can guarantee those two things work next to each other, it supports the sidecar type of application. When we have our main process and we want to have some monitoring or watcher over it, or maybe we have our web server that exposes things in a read-only fashion, but let's say we're working in AWS, we want to share the volume, so we can have another process that will be dedicated for controlling that volume, for example, writing to it. So this way we can completely separate access, but at the same time work around the limitations of the system. So they have to be on the same machine, so the volume is mounted there, and they can see that volume. And when, for example, that node dies, then Kubernetes will, of course, shift the load and understand that, oh, I need to move the volume there as well.
Sometimes pod is often referred to as providing deployment within assuring those containers.
So, a little bit of a, again, conceptual things. So we have our unit of work, the pod. So all the real work happens in pods. Everything else is just superfluous stuff for the management purposes. So what we can do, we can have just a simple pod with a simple container and it will run. We can do better. We can create the replica set that will control how many instances of a particular pod we have. Or we can have a deployment that will create a replica set and a pod, or pods, and will ensure that system will have them up and running, as many as we require, to the best of its abilities. Of course, if we don't have any spare capacity and node died, or multiple nodes died, then we'll have problems. But if we have some spare capacity, then everything works just fine. Or if we have attached scalar, two kind of scalars. Scalars for the pods themselves. We can configure them to scale up and down based on memory consumption, CPU utilization, or custom metrics. We can also scale up and down the cluster itself. So if you're running on Google Cloud, it's very, very easy. You just specify the maximum number of machines it can go up Is AWS, it's slightly more involved. Basically, the cloud formation gets involved, but there is a system, the watcher, that will watch the Kubernetes system and will create additional nodes that will join the Kubernetes cluster and serve the new needs, or it will scale down when there's no need for those resources anymore. Daemon set, as I mentioned, it's pretty much like the a replica set, but it controls the pods on the nodes, and they start first. And the cron job, same. It's a different type of a controller, again, to control the actual things that needs to do the work. And the last thing is a service. Service is just a load balance. Yes?
Quick question, I'm sorry, I came late, so I might have missed this, but pod has one or more containers in it?
Yes.
Is that container, is that a Docker container, or are there other types of container-like things?
Kubernetes can orchestrate Docker containers, Rocket containers, and work in progress to orchestrate the OCI type of containers. Basically, it will orchestrate the virtual machines or whatever else need to be orchestrated. I think it's quite doable because it utilizes reasonable abstractions and can juggle them. So let's look at the guts of the system. So, of course, we have masters, and it's called sometimes API server, and it talks to the kubelet processes working on the actual machines. And usually we would have 1, 3, 10 masters, but we might have hundreds of minions, hundreds of machines serving the actual traffic and actual business purposes. So when we deploy things, by default, even we deploy, let's say, on AWS, but even we open all the nodes for all the traffic from the internet. When we deploy the pods, that traffic, or malicious traffic, cannot reach it. Because Kubernetes create overlay networks, and when we just deploy pods, they stay in, for example, on a 172 subnet, and they are not reachable. The next thing, services. Services, they do have their another subnet they live in. And even it's a flat network, and pod, this pod can talk to this one if it knows its IP. Every pod gets its own IP, so all the containers inside of the pod will share the same IP, but they must listen to a different ports. But that's not recommended because pods are mortal. They are like chicken. You know the analogy, right? Olden days, the servers were like pets. Each had the name. Right? Now it's like, oh, it's a server farm. Well, these pods are chicken. It's on the farm, who knows they're chickens? They come and go all the time. That's why we need services. Service is basically just a load balancer. And again, it's an abstraction, and most widely used implementation is just Nginx or some fancy networks, but in the end it's the same. It listens to the events on the system. Every pod has a descriptor, has a name and labels, and the service basically says, well, I want to load balance against something that has labels matching this. For example, app equal inventory. App will be a label, and the inventory will be a value. So now, that's how it takes care of moving the pods or scaling up and down, or we can do the actually crazy things. You know, we let's say start implementing our inventory service in Java. All Java codes implemented that. It's working, but then somebody comes and say, no, Java is not good. Let's implement it in a node. JS. It's fancy, it's cool. So, a different pod or different deployment can be created to take care of, let's say, Node.js implementation of our service. We'll have completely different deployment schema, everything, but if we give those pods the same label, they will join the pool and they will start serving the traffic for the inventory application. So this way we can migrate from one implementation to another. Again, even we deploy the service, if we use the default settings, those services are not reachable from the internet. They live on a 10.0 subnet, and if you notice, I try to depict that actual nodes live on 192 subnet. Again, you know, to make things useful, we need to expose them. And we want to have load balancers, and we want SSL traffic termination and handling, and the certificates get updated, and we don't want to hunt where the hell we put them these days. So lots of options, but basically, you know, the simplest case, we declare the service as a node port, and then Kubernetes system will provision either a random port from the pre-configured range, or we can actually manage that ourselves and specify the exact port number. And our service will be reachable on that port from every single node. That's the simplest way to expose the service, but it's not the most performant. For the best control over the network traffic shaping, we need ingress controllers, and they're also available, and they can take care of pretty much everything. So again, nothing fancy. It's just a process that listens to events happening in Kubernetes system. It's all etcd. It says, oh, here's the service, and it has a notation. Let's say ingress slash nginx. Then nginx ingress controller will pick it up, will interrogate the description more, and say, oh, it wants to be exposed on host named like that, and it wants to have, let's say, SSL certificate from Let's Encrypt. So I will create a configuration, I will create a virtual host if it deployed on, say, AWS or Google Cloud or advanced resource lake or software-defined data center. It will provision what needs to be provisioned. It will create the DNS entry. It will make call to the Let's Encrypt. It will handle the handshake. Are you familiar with the Let's Encrypt? Who knows the Let's Encrypt? Okay, not many of you folks. So Let's Encrypt is the non-for-profit organization that gives away very, very good SSL certificates for free. Because lots of big companies sponsoring that effort to ensure that internet is secure. Where is the catch? The catch is the certificate is valid for 90 days. And as of now, you cannot have wildcard certificates. They promise they will be available sometime soon, but for now, it's a per domain. So it forces us to automate, and it's geared towards full automation. There's a CERT board, there's a Lego controller for Kubernetes. What happens is that it says, oh, here's the new domain name, or here's the new subdomain. Checks the registry on the account, and says, oh, we don't have a certificate. Let's get one. It's a Acme protocol, and Ingress controller will take care of it. It will send the request to the Let's Encrypt. I'll say, okay, please put this file in this place on a web server that handles that domain. Well, the controller does that because it controls everything. It creates the virtual host. It creates the mapping for that well-known location, puts that thing there. Let's Encrypt makes a call. Says, oh, yep, I see the value. You in control of this domain. Okay, here's your certificate. So we get the certificate. Kubernetes uses those secrets and the config maps to store them and use them to serve the traffic. And then on schedule, we can do pretty much every day, but probably every week is fine. It says, okay, let's see what's going on with the certificates. And if they are needing the expiration date, I think if they are more than 60 days from expiration, then it does nothing. If it's less, then it updates them. So lots and lots of things happening, and we don't have to worry about that. So now let's see what happens when we use Kubernetes to implement our microservice. Yes?
Yeah, so where does this run? You were mentioning the CERT bot does all of these things. Is it running in a pod? Or is it
Everything is a
external?
pod. Yes.
Oh, so it's running on one of the instances of a pod.
Yeah.
And the company makes it available for free. What is the company makes it available for free, the containers, for us to...
Oh, there's several implementations on the GitHub.
Okay.
So the CERT bot, and it's standalone process. You don't have to run it on a Kubernetes. It's just a process that will manage certificates on the machine. They're extension of the same process for Kubernetes that will run inside of the Kubernetes, and because secrets are shared, all we need is the one process that will periodically make sure that we have what we need. Okay? So, let's see what should we do if we want to deploy our microservice on Kubernetes and we want the system to take care of the failovers, roll-ins on rollbacks, and scaling. So we need a pod that will run our MongoDB. We'll need the deployment for the Mongo that will specify the replica set, and the replica set will specify just one instance of the Mongo. We can go crazy and have a full Mongo set up with the shards and everything, but in this particular case, it's a simple application, and one instance will do. However, when we do it this way, we addressed several things. One, the replica set specifies we need one instance at all times. So when Kubernetes detect that this pod is dead, the simplest case, the process exited, but it has also the health checks and readiness checks. we can implement ourselves, and Kubernetes will periodically check for that. So when they detect that process is dead, unresponsive, or health checks are not passing, it will kill it, create a new pod someplace, and make sure that we have our MongoDB available. Now, more interesting things we get from this. Mongo, of course, is fine running, but we'd like to persist our inventory. Right? So we need a persistent storage. Well, here's the thing. If we go, let's say, AWS route, and we use the older EBS storage, then it can be mounted only to one host. Well, to work around that problem and also work around the difference between, let's say, a dev environment and actual production environment, Kubernetes has a wonderful, wonderful concept called persistent volume claim. So what it is, basically when we create our pod, and by the way, let me know if you want to look at the actual pod definition. We'll look at it later. So it specifies that it needs that much storage in either class of the storage, and it will be auto provision, or again, we can use the labeling match. Let's say we want to claim a Mongo storage. So let's say storage equal Mongo. So that's what that claim says. So what happens is that all that definition for production, pre-production, QA, and development is exactly the same. But what's backing that claim is vastly different. When we develop, we don't have EBS on our laptop, right? What do we have? A file system. So, a while back, I showed that, okay, the Kubernetes has the persistent volumes. So we can deploy a definition of the persistent volume there, give it a label, Mongo storage. And in our dev environment, it will be just a file system. In a pre-production environment, it might be EBS. In a production environment, it might be a fancy system, maybe a Ceph, maybe something else. So that plays very, very nice with that immutability concept for the environment. It's pretty much immutable. Once we created that descriptor, it doesn't change when we move things from our laptop to pre-production environments of various kinds and to production. So, so we get the failovers handled for us. We get the volumes remounted for us by Kubernetes. One warning though, it does work, but in AWS case, it works really, really slow. I mean, it will work eventually. And therefore, there are some advanced file systems available. I suggest if you just look at the Rook.io, they do a couple of things. They utilize the storage that gets unutilized on the machines we provision on AWS, and also does the really, really fast failover. So even with the AWS and EBS, it will work. If you need fast failover, then there are options available, but you need to research them. Now, when we have this service, and you see that selector here, okay? This is what says we need to load balance to the pods which the label app equal MongoDB. So now our microservice again, needs the same things. Need the deployment, the name will be inventory. We'll have a replica set, and here we can specify 1, 2, we can auto-scale, whatever we want to do. By default, we can start with 1, and there is a command, like kubectl, scale equal whatever the new number, and it will scale up and down. And the same thing, we have our service that will load balance between the instances. And then we need an ingress. The ingress will finally expose our service to the outside world. So initially it looks like lots of moving parts, but when you start dissecting them, it's like, okay, yeah, kind of makes sense. Volumes, okay, I get it. So if I really care about the volumes, then this Terraform, I can provision the volume. And then Terraform is a resource manager, and it works across all possible cloud providers or software-defined data centers. So if your infrastructure spans local data center, Google, Amazon, and something else, then Terraform can manage your business application across all those providers. So if you, for example, have a failover from Amazon to Google, when you deploy things, you want to do them in concert. So the Terraform can do that for us. And when we, for example, provision the volume, we also work with, let's say, a Kubernetes system and let it know, hey, I just provisioned the volume, here it is, use it. Last piece. Kubernetes do lots of things for us, still not enough. Why? Because Kubernetes abstractions all about one thing, controlling one process. Okay? It's either MongoDB or it's our inventory application. Right? But actual business applications composed of many parts. And when we deploy them, we want to have a consistent configuration, and if we change something, we want that to change everywhere. Right? That's why we need something more. And I couldn't imagine that in my life I will promote Microsoft technology. I still surprised myself. But to be honest, when I start using the Helm charts, they were developed and sponsored by the company called Dace. And Microsoft just acquired them a few months ago. Here it is. I'm promoting Microsoft technology. Nivret knows that. So, what is that? The Helm chart, the actual tool that allows us to create our business applications defined for Kubernetes. Okay, so in our example, it's database, the Mongo database, and our microservice that serves the inventory. Simple Spring Boot, RESTful application or whatever it is, right? But they need to be deployed together, right? Otherwise, we need to use one system to store things, then either by agreement, put configuration, or explicitly map things. So enter the land of Helm charts. So the Helm charts can describe the full system. There's lots of charts available for free. There's stable charts and in development charts, and I will show how custom charts can be created. They describe everything Kubernetes-wise. So there's a simple chart that allows us, for example, deploying Spark cluster with some Jupyter, Zeppelin, notebooks, or whatever hell we want. Really, really complex systems can be deployed really, really easy. But more than that, the Helm charts, they help managing them. So one of the problems I ran into, I experimented with Swarm, I believe. When I want to update just the one thing or a configuration, sometimes it would redeploy the whole thing, not always speedy. So Helm charts, they have two parts. They have Helm, it's a command line interface that we run someplace on some tower. And it has a tiler, that's a server side. That's again a pod, a service that we run inside of the Kubernetes system. And when we deploy our description of something, it's called release, all the resources get created, and then we can update them. We can update parameters, and it's smart enough to understand that some of the things it can do on the fly. Some of the things will require restarts or rollovers or rollbacks. It supports them too. So I would say it plays really, really nice. So when we want to experiment with something, we can deploy our complex thing, but then we'll say upgrade deployment and give them new parameters, and we'll push them there. So for example, if we want to update only one image in one of the components of the complex system, we can specify, for example, new variable, and if this variable signifies the image, it will understand where it's used and will update that thing. Oh, it's just a screen. So, how are we doing time-wise? Well, looks like we have time for demonstrations, live ones. Shall we do that? Yes.
I wasn't clear. Can Kubernetes operate across multiple clouds? One Kubernetes cluster span multiple clouds?
In theory, it's a Kubernetes. They can do that. I never tried it for myself. I just read the documentation. But basically, Kubernetes is the one thing that buys you independence from the cloud providers. So if you rely on a Kubernetes system, then the only difference would be between, let's say, Amazon and Google Cloud. In a Google Cloud, you'll say, give me a Google compute engine and say autoscale yes. Done. Okay? With AWS, it will be, let's say, use kops or some other methods of procuring that, and doing a little bit more jig to enable autoscaling. Then there's also numerous procedures to, let's say, deploy Kubernetes on bare metal. I would probably recommend going with the CoreOS guys, because they're doing a really nice job taking care of the OS. They have 3 parts on the machine, the A and B and the user space, and they really manage updates well at the OS level. Then they provide the scripts to deploy the whole system either on bare metal or in the clouds. Okay, but it's very important to have the OS up to date, and then once you deploy Kubernetes on that, The API is the same. The thing I showed earlier and mentioned the persistent volume claims, that's another differentiator between cloud providers. Again, if you, and you probably have no choice but use persistent volume claims to be able to develop locally. Otherwise, you cannot mount those disks on your laptop, right? So once you're using those claims, then the Terraform can take care of provisioning volumes on those respective systems. They don't have to be exactly the same, as long as they have the same label, let's say EBS or Google file system volume. They will be picked up, selected by those claims, the same way as file-backed volume on a laptop will be selected and used. So this way, I would say probably 90–95% of everything will be provider agnostic. So let's just say, okay, let's run Spark cluster. Okay, that many nodes on nodes of that kind, that much CPU, that much memory. And as long as the provider can give us that kind of machines, we don't have to change the descriptor. We'll just run them.
Were you asking though about like running half of your stuff in AWS and half in Azure, or?
Yeah, I was talking about, let's see, you mentioned failover. You're like, what if you're like the case you mentioned was you're in Google and you failed over to AWS, or maybe more likely the other way around.
Well, it's way more involved process. You want to switch the DNSs and handle that, and then
Yeah, I don't think Kubernetes is split.
it will be two different Kubernetes clusters, and then it doesn't matter if one is in AWS, another in the Google Cloud. Still, it's not that transparent. It's actually not that transparent even inside of the AWS. Those availability zones, the volumes cannot be mounted or remounted from one availability zone to another availability zone. That's where those file systems like Rook.io can help, because they take care of it. Yes?
Does Kubernetes support EFS instead of ETS?
Oh, it supports a whole bunch of,
Is that what
if there is a file system, it supports that. If you're curious about that, let's say,
It's a Java implementation.
Yeah.
see? And it's just officially supported. There's everything in Kubernetes is a plugin, except the kubelet itself. So that is exact spec how to implement something for the file system that's not here. Not all the capabilities available from all those file systems. For example, Kubernetes tries to simplify things, and you don't hear that much about the volumes, like they're throwaway. Then simplest thing, you can define a class of the storage you need, and some of those plugins that they allow auto provisioning of the storage. It actually works with the AWS and Google. If your user has the permissions to provision volumes, then you can deploy your system and say, well, I need that much storage for now, and can specify if those volumes will survive the termination of the system. then we will either provision those things and either tear them down or let them stay. If you really care about things like our Mongo volume, where we want to persist that, then I would say probably I feel safer provisioning that is the resource manager like Terraform, and knowing it's there, taking care of the persistent volume.
So if you're using something like Terraform to provision your instances, how do you then go about getting Kubernetes installed and strapped onto those? Does Terraform take care of like running scripts to install Kubernetes, or are you starting from a core OS image that has all the Kubernetes stuff on it?
It depends. So for example,
How would you recommend or suggest doing it?
it depends. So if you are running your Kubernetes cluster on Google, then you don't probably, well, you can use Terraform, and Terraform use Google as a provider, and we can actually look at that provider. So, there's a whole bunch of providers. So when we go in the Google Cloud, okay, there's a Google Container Engine or Compute Network. So you can say, provision me Google Compute Engine of that many nodes of that kind, and we'll create the whole cluster. CoreOS guys, they have Terraform scripts to create Kubernetes clusters in a semi-uniform way against everything, and it's all Terraform driven. Well, the Kubernetes, they also have provider-specific things for creating Kubernetes cluster. For example, in AWS, it's kops, K-O-P-S, Kubernetes operations, and they pack the configuration in a S3 bucket. I would say you can even manually provision the Kubernetes cluster. Once you have cluster up and running, you just want that to be always operational, pretty much like your data center. It becomes your resource pool, and it can be divided into namespaces, and that's how you probably want to control resources. So then by default, you can over-provision things, and let's say you have, 2 nodes of Kubernetes with just 4 GPU of RAM. You can deploy, hundreds of pods on it. It will struggle, machine will swallow. Not good, right? So, but you can enable for the namespace resource management. And then say, well, in this space we have just 4 GPU of RAM and that many CPU resources. And we can start specifying how much a particular pod wants. There's a default, but we can specify how much. And then, what happens next? Let's say if we run in batch jobs, not the persistent workload, then we give it, and it doesn't have resources to run our job. It will just sit there, pending. Let's say the previous batch job finished, so it frees the resources, it will then run our job. If it's a persistent load, again, the behavior depends on the autoscaling of the cluster. If we configure the autoscaling, let's say in AWS or Google Cloud or our custom provider, then if we try to deploy something and it doesn't have resources for it, then we'll say, okay, let's create a node, let's deploy our daemon sets for the login, monitoring, and whatever else is necessary, and then let's deploy our workload. Any other questions? Yeah.
On Mesosphere, I know when you roll out a cluster, some stuff is fixed, like your masters. You can't add masters later. Agents you can add whenever you want. It's trivial, but masters are fixed. Is there anything fixed that you have to consider when you roll out your Kubernetes cluster initially?
Yeah, you need enough masters.
Can you change them afterwards, or do you have to pick one? Like, you know, like 3, 5, 7?
I think you can. Let's Google that. Yeah, there's a guidance. Yes, to my recollection, yes, masters actually can be added because the most important glue is etcd cluster that holds everything. So that's the most important thing that has to stay up and running, and everything goes there for configuration. Yeah.
You,
It's not finished yet.
That's how you prefix it, but, right? No, your example shows a single microservice, and I was just going to point out that I found that Kubernetes' greatest value is when you have multiple microservices, you're taking your monolithic app and you're broken into a bunch of microservices. And then by being able to, the problem with many microservices is then you have this latency as you call from one service to the next, because those get deployed in different places. But due to pods, deployment infinity, you ensure those things are deployed together. And that's the value I've found with Kubernetes, right, with microservices.
That is actually, I would not recommend doing that. Because you can, anyway, since we're talking about that, I hope we should emphasize that more.
Can I clarify the question? You're talking about deployment of things that are going to call each other a lot close together to reduce latency?
Yeah. So if those microservices get put on different nodes entirely,
Okay.
because you're not necessarily specifying, in other cluster systems, cluster orchestration systems
Right.
allow you to define deployment.
So kind of like proximity.
Exactly.
Say, okay.
Yeah, that's where I found it
So,
really useful.
It is useful, but only when you can pair, let's say, those things in pairs or triples or whatever you can fit into a single container. However, you can control the latency, again, by specifying those preferences and node selectors. When you deploy your pods, you can say, well, I want to run them on a node, and let me explain the latencies. It's just the key value pairs, and there could be a whole bunch of them assigned to the nodes. And let's say one of the keys will be, let's say, rec. Okay? So every node will be marked as the rec 1, rec 2, rec 3. Now, or it can be more abstract, like availability zone, or it can be, I don't know, some network something, right? So when Kubernetes will deploy our thing, then by specifying selectors for the nodes where we want our workloads to run, we can, for example, have them in the same rack, or semi-close on the same fast network. Then there is more. When we have those pods, there's 2 things or 3 things. One of those things might be actual local load balancer that can take care of more optimal routes for the network traffic. And I wanted to emphasize that yes, actually wanted to show them during the demo of this, the Helm charts, but this picture hints that it's not necessarily our microservice and a database. It might be one microservice calls another microservice, or a whole bunch of other services in chains or in parallel. What I will or plan to demonstrate at Helm chart that how it looks like for this particular service, but of course it can be way more complex chart. There's a whole bunch of services. I mentioned one that deploys the whole Spark cluster. There's the masters and the workers and scientists' notebooks. It's a simple chart with a whole bunch of services. Okay, so. Okay.
Can you explain, I guess, when you're talking about, I guess, these components within Kubernetes, high level in Kubernetes, I guess you have an etcd cluster. Terraform, would that be considered a provisioning server?
Terraform is not a part of the Kubernetes.
But it's within the ecosystem. It sits outside of Kubernetes.
It's completely outside. So it's more of DevOps. I mentioned those things like Terraform and Ansible as very nice things to have for your DevOps. They can probably take care of pretty much everything.
Assuming you have bare metal, are you using Terraform? Are you putting agents on your bare metal nodes and I guess core OS nodes?
So,
and I guess what are you installing? How do you install and piecing together or I guess what are the major components within Kubernetes?
it depends on your stuff in IT. So, if you have pretty much constant loads, then you can let them install OS on those boxes and then start from there, okay? Or you can use something like iPXE and boot those servers from ground zero. Basically, you press the reset, the machine comes up, and it loads the image it needs to load. There are a couple of, well, more than a couple systems. It's kind of a old school way of doing things, but it's still really nice if you have big bare metal park of machines. So there's a matchbox available from CoreOS. It's basically a system that describes all your MAC addresses and their capabilities. And then you need a system to build the images, ISO images. And then you query your inventory and say, okay, give me a machines with 32 gigs and CPUs, that powerful. Say, okay, I have that many. Okay, I will borrow 4, and I want to put, let's say, Ubuntu on them. So you know your Ubuntu ISO images. You say, okay, here's the, you correlate MAC address to the ISO image. And then on the racks that IBCM systems, or you physically press buttons. And when machines comes up, it says, hey, I want my IP address and connects to DHCP server. DHCP server, oh, by the way, you should load this. And then you load your image, and the image as OS or some particular pre-configured OS is, let's say, SSH key. Okay, and that SSH key then can be used by, let's say, Ansible to connect to that machine and do whatever is necessary.
Regardless of I guess what's in your spec, that's a minimum spec. You're getting the whole machine, right? It's not splitting off, VMs within a machine.
You can. Again, if we go back to my original slide, so it's actually gets really, really crazy, and sometimes it's useful. when you want to save some money and you're really good at operations. We always need those three things, okay? Computing. We can get that from the bare metal. We'll say, okay, whole machine, that's probably makes sense for production. In, let's say, dev or some sort of a pre-production environment, you might say, well, I don't need that much. I want VM. You're just running multiple experimentations. Again, you can have your open stack running on the bare metal. So it's like a Russian nested doll. you use iPXE to provision, let's say, a whole bunch of bare metal machine. Then again, you install OpenStack and use iPXE to provision virtual machines. And then, in the end, that's a software-defined data center control plane. You say, well, give me a machine. And you can specify if it's a bare metal with a qualifier or a virtual machine. In the end, you will get the OS, is the SSH key and access ability, and you then configure that to whatever hell you want. Or, like the Kubernetes, they try to abstract that even more and run the containers. But again, the Kubernetes, the kubelets, they can be installed into virtual machines or bare metal machines. Nice thing about that, it's fairly easy to experiment and measure and know, if you get any measurable performance gain. By the way, it's very, very important to measure things. So Kubernetes and the Docker, they are wonderful, but network might suck big time. So that's why there are plugins available, but most of the overhead might come from the non-optimal network stacks. Other question? Yes, sir.
You mentioned you can roll back service deployments.
Yes.
Right? Is there any support for doing rolling out new version to, let's say, half of your machines?
Yes.
And then, like, when you know everything is good, you can roll that completely?
Yes, in version 1.7, it supports the canary deployment, blue-green, and whatever hell you want. Yeah, not everything might be there right now, but moves in that direction. Again, as I mentioned, the Kubernetes gives you a great support for doing that type of thing, if even it's not there. Remember the label matching? You can create a completely different deployment that will deploy your new version. It will have the same label, but initially your count will be 1, right? And you can watch, or automatically system can, it will join the same load balancer. Your, let's say, elk stack, the new latest version that basically learns and detects the anomalies. It might see if, the traffic looks okay, then you basically start scaling up your new deployment and scaling down your previous deployment, and you can fairly easily implement that yourself, but it gets built into Kubernetes because it's what people do. Yes?
So what cloud provider do most Kubernetes users use? I take it Google, this is a Google that they take Kubernetes support seriously.
Google Cloud will be the easiest and has a wonderful support for that. It supports automatic version upgrades. It supports auto scaling. It's just a one checkbox. Yes, I want auto scaling. But you cannot say that Google used the most. Actually, Google Cloud usage is minuscule. If you ask me, I'll try to stay away from the Google. I've been in an enterprise for a long time, and what pisses me off the most, they do something and they change it completely. Even they do wonderful job, then they completely change the way it operates, and it pisses everybody off and causes outages. Because people are people and not paying attention. Or sometimes it's like, why? So, if you look at the percentage-wise, it's not that great then. And everybody tries to create the container service. The AWS has that ECR, whatever the acronym is. It's another way of running containers. I try to make it work. It's really, really hard. It's very raw, and I don't know why they implemented that. By the way, there was a question if I will compare that with the Swarm and other things. You know, once I discovered the Kubernetes, and if you look at the history of what the Docker as a company doing, they basically gradually try to re-implement Kubernetes. They I don't know if they have a viable business model, because Kubernetes, well, okay, it's a true plus something, but conceptually, architecturally, in a way they validate everything the Kubernetes do. They start to add those features, but in my books, like, why? I already have Kubernetes. I don't want to sell technology like Docker as a company. I'm a user of the technology to actually deliver the business value. So I need the stability, I need proven things, I need very good levels of abstraction.
And the number of companies that are contributing to Kubernetes versus
Oh, yeah.
Swarm.
Oh, yes.
Would you say that AWS's CloudFormation scripts are also sort of like Swarm, in that they are like a subset of Kubernetes?
No, CloudFormation is the Amazon-specific Terraform. So basically, if you use the CloudFormation, you can switch to Terraform. It will be easier, syntax-wise, I would say nicer, and you will gain, again, ability to do the same things CloudFormation does in Amazon. You can do it in any cloud provider. So that's the Terraform CloudFormation. Yes?
So how do you manage these services, like let's say after a couple of months or year, because it might become very complex at one point of time, because lots of microservices talking to each other. So is there like a UI or some diagram that you can see? Or
This is the live UI. If you like UI, then that's a live Kubernetes dashboard showing the live cluster. And if we look at the all namespaces, well, I'm not doing much, but there's already 20 pods are running. Some of them are system pods, some are DNS pods, this, that, and not doing much. My point is that UI is really, really great when you exploring that. After that, it's probably useless. What you really want is the services like Datadog and maybe Elk Stack is the new things. Then you can probably want to look at the anomalies, things not as usual, whatever it means. And then there's a whole bunch of companies, they try to solve the problem. They, like Datadog, for example, they will give you a great overview. And the demo actually includes integration with the Datadog and running that. But basically, you can also, the kubectl, it's a wonderful command. You can ask for all the services, all the pods, their names, their labels, and you do need to do the audit. You do need to watch your infrastructure. There's the labeling system. You can make it mandatory and check if, let's say, all your pods have, let's say, department level or project level labels, and then you can aggregate them and maybe do the cross charge. Actually, there are companies that their entire business model is to allow the more fine-grained metering of the resource consumption and allocation to the departments or whoever. If you just worry about the resource consumption, then again, namespaces, there are a few of them. You can assign limits to those namespaces, and then whoever has access to that namespace, they cannot consume more than allocated to them. Persistent volumes, deployments, lots of deployments. Let's look at just one namespace. See, it's replica set. See a whole bunch of labels. So the replica set says, well, there's a pod and a service. Okay. So let's look at the name segment. Okay. So this is the example. Well, it's a real thing, but it's a chart that basically YAML file with those things, curly braces. That's the Go. No, it's not the Go. Jinja. I think it's a Jinja templating system they use here. And you see, it basically describes the daemon set, and this is the daemon set. That means this thing that, according to the specification, will be run on every single node if we do not specify node selector. Again, in the Kubernetes land, by default, it can be a very, very small thing, or it can grow complex enough if we need to accommodate resource management and very fine-grained control over where we want things to run. So if we here always specify the label Datadog agent, and we'll say this will be a spec for the pod, and you see containers as a plural, and the first one will be based on this image. And then we specify the environment for this container. Make sense?
Do your labels dictate which node it runs on? Is that, you mentioned before you can direct applications to nodes with labeling and stuff. Was
Yes.
that label you meant there? So it'll look for a DD agent labeled node, or when it
Well,
deploys?
these labels are for the pod. There will be a separate node selector.
Okay.
And the node selector always works by label matching, and there's a simple label matching, like exact matching. There's a regular expression matching as well.
Just prior to this, you had the GUI up there, and I'm just curious, does the command line interface support most of the GUI stuff? Because it has a CLI, right?
Mm-hmm.
Does it support most of the stuff that the GUI does? Because I generally go to the CLI more than the GUI. Especially for
I
script
tend
defined
to
things.
work with the CLI the most, and actually this ID, like this Helm chart, once you get used to it, then it's actually easier to do it this way than the UI or the CLI directly, because IDE is smart enough to understand the syntax and show you right things.
Yeah.
Even this descriptor, we can come to here and let's say go to the deployments, and we can edit it right here. And we can reapply that. However, there is no syntax control, and you have to look at the documentation and, you know. Nice sometimes for the quick change, like, you know, replica 1 to 2.
Yeah.
Right, but it's right here. But in general, you know, I'm not a big fan of doing things manually. It's all about automation in continuous integration, delivery things. So, by the way, why it is useful to have a chart. So, the chart, okay, this chart can be used by any company, anywhere. Only thing we need to customize is our unique key for integrating with the Datadog. Okay, you don't want your data to be mixed with somebody else's data. That's why when you open the account with the Datadog, you get the unique key, right? But hard coding the key also not so good, because we might have want different accounts for pre-production and production for the Datadog, just to separate things by volume. You know, when we start looking at the real data centers with the hundreds of machines and resources, the space gets crowded. So, what the Helm charts give us? They give us that template that describes the essence of the thing we want. And they give us ability to customize that according to the circumstance, basically. And here's how we use this chart. Okay? We'll say Helm install this Datadog, and Datadog refers to this directory. But again, in the enterprise, you know, pretty much like we use Maven and we host our dependencies in repository. Same goes with charts. We can start a chart server, and we can deploy charts there and use charts from them. And we can declare dependency of one chart on another chart. Same dependency management we take for granted with the, you know, these RPMs and Maven. It's also available here through the charts. And we can specify our things. So let me go to the Datadog. Okay. So one of the services, you know, if you don't have sophisticated operations, then I would say it makes sense to subscribe for that and have lots of optics into what's going on. If your staff is more knowledgeable, then there's great things you can deploy in-house, like Prometheus or Elk Stack. Again, you can even deploy the Elk Stack on Kubernetes and have them multiple stacks. And so it has lots of things, and let's say look at the Kubernetes dashboard. A whole bunch of Kubernetes integrations. There's nothing. Okay. Okay. So. Let's see my script. I should go. Logs.io, by the way, another service that they have a hosted Elk stack, and if you don't want to manage that yourself and okay shipping the logs there, another wonderful service. Again, there's these days it's just dreams come true. If you have a startup and you want to couple something together quickly, there's so many good things available. By the way, we used Helm, and let's say, if you, okay, now, gives this list of the things we deployed on Kubernetes. It gives the revisions, and you see that Nobby Monkey has 14 revisions. This one has 8, and this is the GCloud chart. This is the KOM API gateway. It's my experimentations, but there's the Helm. We can upgrade, and we can roll back. We can roll back to the revisions if something goes wrong. And I'm not suggesting we should do it manually. You know, whoever manages that checks the health of the system. Something goes wrong, let's roll back. Now, probably should have been showing you the. Okay, now we got the daemon set. That's Datadog agent, and by now we should have our okay. Now data starts to flow there, and now we see, you know, some of the things. We have 15 pods running on the nodes, and 7 on another node with just 2 nodes clustered. And we can kind of watch the CPU utilization. There's infinite customizability to those dashboards. Okay, so we have our integration going. Now let's look a little bit at Terraform. So what should we do here? Okay. Okay, so Terraform, again, if somebody is used to UI, might scary initially, but actually if you use IDE, then IntelliJ fully supports and understands the template, so it provides a good UI. But it promotes the immutable infrastructure, the declarative structure. So here, I said, you know what? Let's look at the Terraform definition here. And again, there's a reusability all over. We can define the modules. Like, Terraform, again, is a resource manager. And I probably mislabeled that like AWS and GCloud and local. It should be dev, QA, and production. Here's the module that defines the persistent value claim. Okay. This is the Terraform working with the Kubernetes as a provider, and says, you know what? You should have a persistent volume claim on a volume with this name, Inspur-Mongo. Okay? And then in a different environments, we provision that volume different way. So in AWS, okay, also we use 2 providers. the Kubernetes and AWS. We specify the region or regions. And we'll say we need this resource, and resource from AWS, EBS volume. Size will come from the variable, and that can be overridden on the command line. And we use this module in this context, and we override the default value that we have for the storage inside of the module. So when we're using modules, we can override everything we need for this particular circumstance, but still it can have a sensible default. So when we say Terraform plan, it's just a dry run. It says, well, I will do this if we go apply. Okay. Now Terraform will be busy actually creating the EBS volume. Logging into console, we will see that there. And when it creates things, we can create the config files to drive, let's say, Ansible inventory or anything else we need. Okay. So let's look at the Kubernetes console. So here, I should have shown you before there was no this volume. Okay, but it was just created, see, 25 seconds ago when we did the apply. But again, the Terraform can manage those things across multiple providers. So, and it's bound, and there's a claim. Okay. Now we're ready, we can deploy our application. So, let's see my cheat sheet. All right. So, the Helm serve, this command will start the local chart service. Normally, in production, of course, you will run that independently as your registry, pretty much like you run your Artifactory for various Java and non-Java artifacts. The same way, you can run the chart service that will hold, let's say, common charts. You know, what would be a common chart? Let's say Postgres or MySQL database, right? You might want to create it periodically for various services for the testing purposes. And whatever the versions you want to be consistent, you put it in the chart, update the chart, everybody using the same chart or the same version of the chart, and you know what you're getting. Okay. Let's put this in the background. See, now it's certain charts on that board. So here's the So, what happens here? Remember our little diagram? So we have our service, okay, service that depends on the Mongo or another microservice. It doesn't matter. In this case, the chart for deploying Mongo database or another service, it's our dependency. We depend on that. When we run our thing, we depend on another. It can be a database, it can be anything. And in Kubernetes land, it's all pods. So, and by the way, the inventory app is the standard Spring Boot app. It's nothing too interesting to it, but once we build that, we have our build script to create a Docker image and put the Docker image in a repository. And what's changing as we rebuilding things, well, the tag for the image changes all the time. So, before I discovered the charts, I was using Mustache's templates with the Python and doing a whole bunch of Python scripts. But Helm charts eliminate that need. So here's our Inspur Mongo chart. And again, chart has descriptions, nodes, automatically substitute the values. It basically describes our deployment, okay? And here's the thing, okay? This is the deployment, the thing that will work. We'll specify the replica, one, but we can scale it later or auto scale. And you see all those things, the image, okay, is the variable, and the body tag is the variable as well. And by default, they are specified here, right? Make sense so far? So this is our chart. We can, every time we need our little Mongo database, we can say, okay, let's install this chart. We'll get the chart installed and we'll have a new release name. And because in our deployment descriptor, and for the service, we include the full name, that template with helpers. The full name includes the release name. Every time we install the chart, we get the new instance of the Mongo database. So it's great for testing and throw away things. And here our app. Again, same thing, we create a chart. The one thing that differentiates this chart is that we declare the dependency. So our chart depends on Mongo. That's why we update the dependency. Okay, good. No, you can stop me anytime. So the last thing, if you want to wait for that, is basically a deployment of the thing. So again, lots of help from Helm. We can inspect and install. Okay, and let's see live. You see, it shows that we get the Alexandra Kumi, the name of the release, and you see it's in progress. The replica set, now it's pulling the image and it's creating the containers. Eventually it will be there. The original plan was to, actually I have a script to JMeter that will try to get the inventory, and I wanted to demonstrate how I kill the pod and it gets deployed on a new node and everything continues as nothing happened. But we're out of time. By the way, guys are great. You stayed so late.
We can keep going. Just a lot of people don't feel.
Well, the facility probably wants to close.
Yeah, I think 9 o'clock is kind of our limit here, so you got what, a minute or two? If you want
But,
to
you know, we can continue conversation,
Yes,
over
we
the
can.
years.
Yeah.
I'm not leaving if you have any questions, and, you know, that was my contact email, and you can always Google for my name and ask me any additional questions or invite me for the talks or whatever. Yes?
Is the video presentation going to be available on the site?
Yep, it's gonna be on Vimeo. I've got like 60 videos if you guys spare time.
Okay.
Go check them out.
And I'll give Nimrod the PDFs.
Yep.
So
Be on cj.org.
will be available as well.
Thank you.
Thank you for doing that.